Good morning, sir.
Today we are going to discuss one more planning technique which is called as graph planning technique. Before going further, let us recall we are discussing different planning techniques, that is problem solving techniques, which are used for solving more complex problems, like if you are programming a robot like a rover. So for writing program for robot navigation, you will have to use this type of problem solving techniques. So these techniques we have categorized into two categories. One category is linear planning technique like goal stack planning, and another category of planning techniques we have put them in the category non-linear planning techniques. Okay, so in goal stack planning we saw we follow the order in which sequence of actions will be carried out, and we will have to follow that specific sequence. We put operators and those actions on the stack and we remove them as and when they are satisfied. Therefore we call them linear planning techniques which follows this type of strategy. Sometimes it is not possible for us to define in advance the order in which you are going to tackle the sub goals. So out there you need flexibility. So list commitment strategy we have incorporated by defining partial plans, and the techniques which incorporate that is called as plan space planning. In plan space planning we work on partial plans and finally we arrive at a solution. The solution will define you set of actions that you will have to perform to achieve the final goal. During this process we work on partial plans in flexible manner, and therefore we call this nonlinear planning technique. Today we are going to work on another nonlinear planning technique that is called as graph plan, and finally today we are going to summarize this nonlinear planning with constraint propagation concept. Okay. Before proceeding further, do you have any question based on whatever we have discussed in earlier lectures on planning? If you have question, then we work on that and then we will continue further. Any question on goal stack planning or plan space planning? If there is no question, now we will move further. In goal stack planning, we saw that it's a state space planning technique, that we start with starting state and we move to the next state until we reach to the goal state. So that is very similar to like state space search that we have discussed earlier. In plan place planning we work on not state, we work on partial plans, and finally we find out the solution which is a complete plan. In graph plan you are going to develop a planning graph, and this technique was proposed in 1997 at CMU, Carnegie Mellon University, by Blum and Frost. They have proposed this graph plan technique. What we do in graph plan, instead of searching for solutions either in state space as that of goal stack planning or plan space as that of plan space planning, we construct a structure and we call that structure as a planning graph. This planning graph we develop step by step by following step by step mechanism which will capture all possible solutions, and finally it will proceed to search for the final solution in that planning graph. So first we are going to develop a planning graph, and then in second phase of this algorithm we are going to search for the solution in that graph. So we are going to discuss both these steps. In this planning graph, it merges the state produced by different actions, that means operators, which are applicable, resulting in set of prepositions expressed as a single layer. So we have set of prepositions and set of actions. Actions, they require input. So input to the actions, again that is a set of prepositions. So we are going to define that as a layer. We will merge all those prepositions, so that will define a preposition layer. Then we are going to apply these prepositions as an input to the corresponding operators or actions. So we are going to merge all those actions in that graph. We are going to call that as an action layer. Whenever action is performed or operator is applied, that produce the effect or result of applying that particular action. So that is again a preposition or prepositions, set of prepositions. So all actions, they will result in set of prepositions. Again we are going to merge all of them in a layer called as preposition layer. So we have here alternate preposition layer. Suppose I call this preposition layer as P, then action layer, again preposition layer, action layer, preposition layer, action layer. In this way, finally we will have prepositions, set of prepositions as an output. This preposition layer will merge all the prepositions which will be input to the set of actions which we have defined in the next layer. So after performing this action, that will result in again set of prepositions. So all these actions in this action layer, they will result in prepositions. So we are going to define that as another preposition layer. So we will have here alternate preposition and action layers. So therefore this planning graph is a layered graph made up of alternating set of preposition and action layers. The first layer, that means that will be the input that shows all the prepositions which are true. Okay. So first layer in this planning graph, that will be a preposition layer. We suppose I denote that as P0. So in this preposition layer P0, we will have all set of prepositions which are initially true. So initial state is always given to you. So set of prepositions which are true in the initial state, that will belong to preposition layer P0. Every action has a link from each of its preconditions. Okay. So after preposition layer, this is the input given to the action layer. Action means what? Operator. Always remember that whenever we say operator or action, suppose I have action A. To perform this action A, you need to have certain precondition satisfied. So here the requirement of A is set of preconditions. Okay. We define that as preconditions, and after performing this action we have output, that means result. Okay, we call them effector. That means prepositions which are true. Okay. So every action has a link from its preconditions and a link to its effector. So for example, action A has preposition or precondition, that is, suppose P0 and P1. So this P0 and P1, this preposition has to be true to perform this, suppose, action A. After performing this action A, suppose that results in preposition P2. So what this planning graph incorporates in its representation, the action, for example, action A in action layer will have a link from its precondition. Now to perform A, precondition is P0 and P1, these are the prepositions. This capital P0 is different, this is preposition layer, this is action layer. Small p0 and p1, these are the prepositions which has to be true to perform this action A. So we will have a link from preposition p0 to A, p1 to A, and link to its effector. Now effector of A is, that means the preposition which is true, that is p2. So again we will have set of prepositions defined in the next layer, p1 suppose, in which there is a preposition p2 defined. So we will have a link from A to P2, because what now this graph is representing, A is an action for which P0 and P1 has to be true. P0 and P1 are preconditions which has to be true to perform this action A. After performing A, P2 will become true. So therefore we have shown link from A to P2. Okay, so therefore we are saying every action has a link from its preconditions and a link to its effectors. Now again, effectors, they are of two types. One is effect plus, another one is effect minus. One set is effect plus and another set is effect minus. We will see that afterwards. Prepositions at consecutive prepositional levels are linked through no-op. That is a special preserve preposition. For example, suppose there is another preposition P3, and suppose we want this P3 as it is at layer P1. So we are going to define a no-op operation. Uh, Simply, suppose I denote that as a dotted square. So which will simply copy this P3 to the layer P1. So this special type of operator is called as no-op operator, which will just carry preposition to the next preposition layer. Every two layers correspond to discrete time. For example, P0 layer, preposition layer, and A, action layer, that corresponds to discrete time. That means the objects or prepositions, they are not going to change during the transition from P0 to A. So time interval is, this is time interval T0, time instant T0, this is T1. So during T0 and T1, objects, they will not change, they will not transform. Similarly, from A to P1, action layer A to preposition layer P1, this is time instant T1 and the P1 corresponds to T2. So during T1 and T2, objects, they will not change. That means action will not change, or prepositions, they will not change. So we call this discrete time. Prepositions in one layer, that cannot be true simultaneously, and actions in a layer, that cannot happen simultaneously. We are going to define that as mutex in each layer. We will see this afterwards. we introduce edges between actions in a given layer and each of its effects in the next preposition layer, just like this. We have introduced a link from A to P2. Why? Because after performing action A, that is making this preposition P2 true. So that is the result of execution of action A. So therefore, edge has been introduced between A and P2. Okay, understood up to this point?
Yes, sir.
What we are trying to understand in planning graph, we are trying, first step is, first part in this algorithm is how to develop a planning graph. So to develop a planning graph, we have seen that we have to add prepositions and action layers alternatively. How we are going to do that? We will have, we will be given set of actions corresponding to the given problem domain. For example, if it's a block world problem, so actions are in block world problem. Anybody can recall one of the action?
Different sizes.
Action operators. Operators which you can use in block world problem to achieve a goal state. Pick off, block X, pick off, put down, these are the actions, right? In block world problem. Then stack and unstack, these are the actions. Robot hand, arm performs these actions. Okay, there is a robot arm. So stack and unstack, pick up and put down. These are actions, and these actions, they have preconditions which has to be true. To perform that action, there is a requirement that we write on the left hand side of a rule, and the result of performing that action we write on the right hand side of the rule. Now this is an example of a simple planning graph. So as we have seen, we have alternate preposition and action layer. So first we have preposition layer P0, then action layer A1, preposition layer P1, action layer A2, preposition layer P2. Sample graph is shown out here. In preposition layer P0, that is first preposition layer, we will have set of prepositions which are true. So here in this graph, P1, P2, P3, P4, small P1, P2, P3, P4, these are four prepositions which are true initially. That is given in the problem. Initial state is always given in the problem. Then we have action layer A1. In action layer, you can see here two types of symbols have been shown. One is a solid green color block and another one is a dotted hello rectangle, square. Okay. Solid green color block is showing the action, and hello square dotted block is also showing an action, but difference is this dotted block is defining no op operation. What no op action perform? No op action just copies preposition from one preposition layer to the another preposition layer, so that other actions in the next action layers, if they require that preposition, they can use it. For example, preposition P4 is just copied out here, so that will be available here as it is because of this no op operation. Another no op operation is defined for P3 to make it available out here. P2 is available here. Okay. This is P1. ठीक है. So This is action layer. In action layer we have actions. So alternatively, now P1 layer, which is a preposition layer, where we have prepositions. So how these prepositions are generated? Either they will be from no op as it is copied from the previous preposition layer, or that will be the output of action, result of performing action in the previous action layer. For example, suppose this is action A1. So after performing A1 here, that has resulted in P4. This is P4. Uh, then this is P P3 and this is P2. Okay, and this one more is there, three different prepositions that are resulted after performing this A1. Suppose I define this as P7. Why it is P7? Because here it is P7 and this is no op operation. So after performing A1, result is P7, P4, and this is minus P2, that is not of P2. I will tell you what is this. First define now this action A. Preconditions for this action A are, yes. Now what are the preconditions you can make out? To perform action A, what is the requirement? A1. This is A1. What has to be true? Hurry up. To perform this A1, what are the preconditions? A1 is connected to the previous preposition layer. Look at this. P4 and P1. So P4 and P1 has to be true. So these are the preconditions for A1. P4 and P1. After performing A1, what are the effects? Which preposition will be true? Set of prepositions. A1 is connected to P7. So effect of this is P7, P4, okay, and this P2, but out here you see here a rounded edge has been incorporated out here. So that represents not of P2. So this is another type of edge. In this graph you can see something like this, a line with rounded circle end. So that indicates that negation of the given preposition. So meaning of this is, if you perform action A1, output will be P7 will be true, P4 will be true at the same time. This is connected to P2 but with a rounded uh, end. So therefore that is equivalent to not of P2. So P2 will become false, right? So what we do, we say that this is a set effect plus and this is another set that we will define that as effect minus. So in effect plus we will have set of prepositions which are true, and in effect minus after performing A1 we will have set of prepositions which are false. So therefore after performing A1 we will have P4 and P7 true and P2 false. Okay, then again we have action layer out here. This is now action A2. Now tell me what are the preconditions for A2, for this action A2? What prepositions has to be true? Pardon?
3.
P?
3.
Right. This A2 is connected to the previous preposition P3. So P3 has to be true. So precondition is P3, correct. Now, after performing A2, what effect plus will contain this set? P2.
P3 and P2.
A2 is connected to P3, that means this line, right, and this P2. Okay, correct. So effect plus will contain P3 and P2. These two prepositions has to be true. And one more link is there going this way in between. That is P3. Okay, P3 is repeated. No? We will give some other name. P6. P6 is also there. Suppose call this P9. Okay. So effect minus will contain. Now
P9.
this P9. Out here there is a solid circle at the end of that edge. So this P9 will be false. Okay. So not of P9. So effect minus will contain not of P9. Again we have action layer. Again preposition layer P2. So in this way a planning graph is prepared. Now let us move further. We will define all the components of this planning graph now. Now this planning graph is a layered graph which will have alternate layers of prepositions and action nodes. P0, A1, P1, A2, P2, A3 up to AN and PN. Every preposition P belonging to preposition layer PI, there is a special action called as no-op that belongs to AI plus 1, that is action layer AI plus 1, that carries forward preposition P to preposition layer Pi plus 1. So no-op operation we have seen. This no-op operation that carries a preposition P4 to Pi plus 1. So it was belonging to P0, right? Now because of this no-op, this P4 will be available out here at Pi plus 1, that is P1. P4 is again available to the next layer because out here there is a no-op operation available. There are four kinds of edges. One is called as preposition edge from preposition Pi to action AI plus 1, linking a precondition Pi, which is a preposition, to an action AI plus 1 with solid lines. So this we have seen. This is that type of edge. This edge is called as preposition edge. Then we have positive edge. That positive edge will be from action to the preposition. So from action AI to preposition PI. Linking an action AI to the to add effect PI of AI. Again solid line. So we have a edge something like this, from action to preposition, solid line, action to preposition, which is the effect of performing this act. This is called as positive edge. Negative edge, from action to preposition, linking an action AI to delete the effect of preposition pi. So solid line with rounded head. Just now I told you solid line with rounded head. So which deletes effect of that particular preposition. So meaning of this is that particular preposition will become the false. Okay. Again recall, if you perform action A1, that will result in negation of preposition P2. So that we have shown line with solid circle attached with that. Similarly, after performing action A2, that will delete this preposition P9. So that means negation of this P9. And one more type of edges you might have noticed in this planning graph, uh, curve, dotted curve lines. For example, this one, right? This type of edges between prepositions and between actions, they are called as mutex edges. Okay. Mutex edge linking two prepositions in the same layer or two actions in the same layer. Thick dotted lines we have used for representing mutex edges. Now this concept is very similar to the concept that you might have studied in operating system risk management. We will see what is that. What is a mutex relation between prepositions and actions. Mutex relation identify pair of action or prepositions that cannot be present in the same layer in the plan. So that means if we have mutex edge between these two prepositions, for example P7 and P2, there is a mutex edge, dotted curve. So that means P7 and P2, they cannot occur, they cannot be true at the same time. Similarly, out here between P4 and P9, there is a mutex relation. That means P4 and P9 cannot occur at the same time. Same way, in actions also we will have mutex relation. Like this no-op operation and this action A1, there is a mutex edge. So that means these two cannot occur at the same time. We will see why. Okay. Now two actions or two prepositions. First consider two actions. Two actions, suppose A and B are actions. A and B. In the same layer, they are mutex if one of the following situation holds. One is if they have competing needs. This is very important. How to identify mutex actions as well as mutex prepositions when you are going to develop planning graph. So two actions, they are mutex if they have competing needs. What is competing needs? If there is a proposition PA which is a precondition for action A, consider this situation. Suppose we have action A and its precondition is preposition PA. Then we have action B whose precondition is PB. PB is a precondition for action B, such that PA and PB are mutex in the preceding layer. Right? There exists a preposition PA belonging to action A and preposition PB which is a precondition for B, such that in the preceding layer, that means previous layer, if these two prepositions are mutex. Now when two prepositions will be mutex, for example, if this PA is P and this PB is not P. Okay. So requirement of A is P and requirement of B is not P, because PA and PB, these two prepositions are mutex. Therefore, you cannot have both of this A and B occurring at the same time. Either A will occur or P will occur, because they are competing the need, their need. So that is called as competing needs. Now inconsistent effect. Two actions are mutex if they have inconsistent effect. Effect, that means result of performing those actions. There exists a preposition P such that this P belongs to effect plus of A. So A is an action. This P belongs to effect plus of A. And P belongs to effect minus of B. There is another action in the same layer. Okay. And this B is belonging to effect minus of B. So what is meaning of this? That will delete this P. So that means after executing B, that will result in not of P. So if you execute A, result of execution of A will be P, and if you execute B, result of execution of B is not P. Right? So this is called as inconsistent effect. So if this is the case, then A or B are mutex. Either A should occur or B should occur. Both cannot be true at the same time. Why? Because there is a reason. If you execute A, result is P. At the same time, if you execute B, that will delete this P. So ultimately, there is no operation performed if you perform both A and B together. So either you perform A or you perform B. So if this is the case, then we will show that this A and B are mutex actions. So we will show relation like this. Third possibility is interference. Now what is interference? Two actions are mutex if they are interfering with each other. That means there exists a preposition P which is a precondition of A, preposition P which is a precondition of action A, and preposition P which is uh, effect minus of B. So that means that will delete this P, that is belonging to effect minus of this B. Okay, that is called as interference. There exists a preposition P which is a precondition of A. A is an action. Another action B we have. Out here, this P is deleting this P, or B, if you execute, then the result of that is P will become false. So this is called as interference. If this is the case, then again both A and B are mutex with each other. So either A should occur or B should occur. Why? Because to perform A, you need P. If you execute B, that will delete this P. So if you execute both of them together, what will happen? Nothing will happen. Okay, because P was there, so B is deleting this P, right? So if B is deleting this P, that means P is negative, so A cannot be performed. If to perform A, you need P. So if you perform B first, then P is negative. Negative means what? P is false. So A cannot be performed. If you perform B, then that is deleting this P. Okay, so therefore we should not execute A and B together. So we will show them they are interfering with each other, and we will show that as a mutex relation. So if, again I am repeating, two actions, they have competing needs. That means their preconditions are mutex. That means requirement of A and requirement of B. Here requirement of A is P and requirement of B is not P. So they have competing needs, so they are mutex. Second possibility, inconsistent effect. Inconsistent effect means if you perform A, if you perform preposition action A, its effect plus is preposition P. If you perform action B, then in its effect minus we have preposition P, that means that will delete this P. Okay, so therefore we say that they have inconsistent effect. They are interfering with each other, so they will be mutex. They are interfering with each other if the precondition of A is P and effect minus of B is not P. That means if B is deleting this P, in that case we say that they are interfering with each other. So show that both are mutex actions. Okay, understood up to this point? Any question?
No, sir.
Now fourth one, there exist prepositions P, which is a precondition of A, and preposition P which belongs to effect minus of A. So we have action A, our so to perform, when you perform action A, that is deleting this P at the same time. Also, if P is a precondition of B, then that is again deleting this P. So if there is an action which is consuming this P, then we say that this A and B, they should not occur together. So that belongs to the prepositions. Preposition P, which is a precondition of A and effect minus of A. And similarly, that is applicable for action. If this is the case, then we say that those two actions are mutex with each other. So A and B, we will show they cannot occur at the same time. Now, how to build a planning graph with these components? You start with preposition layer P0. Preposition layer P0 will contain all the prepositions which has to be true. So that will be given in the initial state. And then you are going to extend this graph. You add actions in action layer A0. Then result of that you put all of them in preposition layer P1. Okay. So that will build a planning graph. So what we say that a graph we are going to extend from action layer and preposition layer by adding action layer and preposition layer. So what we do, it begins by copying two preceding layers and then adds any applicable actions and effects. Then links to the preconditions and effects. For example, in P0, we will have all prepositions which are true initially. Then we have actions in action layer A1, for which you need certain set of prepositions which are true. So you are going to show the edges from P0 to A1, actions in A1. So that will result in effects of actions in A1. So that we are going to add in preposition layer P1. Okay, so we will have prepositions here. That will be the result of performing actions in this A1. Some of the prepositions you need as it is from P0, so you copy them with no of actions. Then using prepositions in P1, you add actions in A2, perform those actions, that will result in some of the effects, that will be prepositions. You merge them, you are going to call them preposition layer P2. So in this way we extend this planning graph. After this we compute a fresh mutex relation between the actions and prepositions. Just now we have seen how to identify mutex relations. Then this process of adding layers will continue till any of the following two conditions is achieved. One is the newest preposition layer contains all the goal prepositions. That means the last preposition layer that we have added, if it contains all goal prepositions, which is a goal that we have to achieve, then you are going to stop, and there is no mutex relation between any of its goal prepositions. Of course, that has to be true. That means if one preposition is true and another one is false. So how to identify that? If there is a mutex relation. So in that particular case, that sub goal will not be true. So we don't want that. We want all goal prepositions as well as there should not be no mutex relation. This is one condition. Second condition, when that graph is leveled off, then you stop this extension. So what is leveling off a planning graph? For two consecutive levels, for example pi minus 1, preposition layer pi minus 1 and pi. If prepositions are identical with same mutex relation, mutex relations at preposition layer pi minus 1 same as that of mutex relations in preposition layer pi. That means prepositions has to be same as well as mutex relations has to be same in two consecutive levels. If that is the case, then we say that we should stop extending the planning graph. So that will be the complete development of planning graph. So again I am repeating how to build a planning graph. You start with preposition layer P0. How to define P0? You will be given initial state of a problem. So all prepositions which are true, that you are going to put in P0. Now how to define A1, action layer A1? We have set of actions given. For example, if it's a block world problem, then put down, pick up, stack, unstack, all these operations are given. So you identify which actions you can perform with this initial set of prepositions. So you put those actions which you can execute right now with this available set of prepositions in action layer A1. Okay. Random आवाज. So start with P0. In P0 we'll have all prepositions which are true, which are given in the starting state of a given problem. Then set of actions. Identify set of actions which you can perform with this starting set of prepositions. Add them in layer A1. Then we will have preposition layer P1. In preposition layer P1 we will have set of prepositions. Now how to identify set of prepositions in preposition layer P1? Because we have actions here, so effect of performing these actions in action layer A1, that will be in P1. Okay, in addition to this, if you need some prepositions as it is, then you can add no actions out here, so they will be available at P1. Okay, so in P1 we will have prepositions which are true after performing this action A1. Now we will have new set of prepositions at P1. Now you identify set of actions that you can perform with these prepositions which are true at P1. Okay, so that will define your A2, action layer A2. So in A2 we will have actions which I can perform with the set of prepositions which are available in P1. There might be a case that there is some action for which you need a preposition which is not available in P1. So you are not going to add that action in A2. So in this way you will be adding layers, extend this graph by alternatively adding preposition layers and action layers. When to stop? When you have all goal prepositions in that preposition layer with no mutex relation between them. That is one situation. Another situation is if two preposition layers, consecutive preposition layers, which we have alternatively available, if they are same. Of course, mutex relations also has to be same in those preposition layers. If they are exactly same, then you stop extending this planning graph. Okay. Understood up to this point? Any question? So if there is no question, I will move further. I will put that in the form of an algorithm. A planning graph of depth k will have k time steps and may have multiple parallel actions per time step. We make a plan graph of depth k, search for the solution. If we are succeed in that, we return the plan. Otherwise, we extend that for the k plus 1. So we increase the depth by 1, just like iterative deepening approach. Then we will go to the step 1 again. We are going to search for the solution in that. If we get, we will stop, otherwise we will extend it further. So that's how in general this graph plan algorithm works. So that was the first step, that developing a planning graph. Now second step in this algorithm is how to extract the solution. how to extract the plan. Developing a planning graph is one step. From that graph, you will have to find out set of actions that you need to perform to get the result, to get the solution, goal state. That is your second step. So here we have two options available. To extract solution, you can use Boolean CSP, that is constant satisfaction procedure, to solve the problem, or you can use a backward search process like DFS to get the solution. When all goal prepositions exist in a layer are non-mutex, okay, that means now your graph development process has been completed. Then perform depth first search DFS, in which that will regresses the goal states to the sub goal states like a backward state space search. This is the simplest way to extract the solution. Now backward search, this call will terminate either by reaching to the first layer, that is P0, with success, or it may result in failure, that means no plan exists. If there is the case that you reach to the preposition layer P0 and no solution, you extend that graph to the next level, that is K plus 1. Again I am repeating, two options are available once you develop a planning graph. How to check out that you have developed a planning graph? Two preceding preposition layers are same. If that is the case, then development of planning graph is completed. Now to extract the solution, either you can have Boolean constant satisfaction procedure or backward search process like depth first search. So you start with the final preposition layer, that means all goal prepositions, go back to the previous layer, that means sub goals, by using depth first search until you reach to the initial preposition layer, that is P0, and the action and preposition that you have followed during this DFS process, that is the solution to the problem. So therefore we have said once you reach to layer P0 with success, then terminate the process. Otherwise extend the graph for one more level. Again repeat the procedure. Now let us put all of this by solving this particular example. We have to prepare a planning graph. Problem is have cake and eat cake too. This is the goal, that I should have a cake and I want to eat cake too. So initial state is defined, that is have cake, and goal state is defined, that I have cake and eaten that cake. So these two preposition predicates have been added, prepositions have been added. Have cake has to be true and eaten cake has to be true. That is the goal that has to be achieved. What is given? Have cake is given to you. So have cake is given and you want that have cake and eaten cake is true. Two actions you can perform, eat cake and bake cake. To perform eat cake, precondition is that you should have a cake, right? Unless and until you have cake, you cannot eat. So that is the requirement for performing action eat cake. After performing this action, output result will be that you will not have cake, so not have cake, and you have eaten the cake, that will be true. Okay. Bake cake is another action that is given to you. Requirement for bake cake is that you don't have cake. So not have cake is false, that means. If you don't have cake, then you are going to bake a cake. If you bake a cake, result will be you will have a cake. So have cake will be true. Okay, so eat cake. This eat cake. This is an action for which precondition is have cake has to be true. If you perform this, result is, that is effect plus, result is effect plus is eaten cake is true. Okay, and effect minus what is false? Have cake is false. Have cake is false. That means this is false. Similarly, for bake cake, precondition is that you don't have cake. Effect is you will have a cake. So have cake is true. Now let us develop a planning graph. Start with P0. So now find out prepositions in this layer P0. Yes. What will be preposition in P0? Anybody? Start with fourth layer P0. So what set of prepositions we will have in P0? Prepositions which are true. So what are those prepositions?
Have a cake.
Right. Have cake is given, that is given to you. That have cake is true. So we'll have this preposition have cake in P0. Correct. So we will have this have cake in this P0. In addition to that, we may need another preposition which is true, but eaten cake, because that should be available later on for the action. So have cake is a precondition for eat cake, right? So in action layer A1, what action we will have?
Eat cake.
Correct. Why? Because its precondition is have cake, and have cake is available in previous layer. So action is eat cake. Now for eat cake, precondition is have cake. So there will be a age from have cake to eat cake. Okay. The result of execution of this will be that you are going to add in preposition layer P1. So if you perform this, effect plus is eaten cake, right? Eaten cake is true. So here eaten cake, and not have cake, that is also true. So not have cake. So in this way you extend this that I have shown in the next slide. You are going to start with, sorry, you are going to start with P0. So in P0 we have cake. Okay, then in action layer A1 we'll have corresponding action. So we have started with level 0. one thing you can do, that how this eat cake will be available. So you can start with not eaten cake. Because not eaten cake is true initially. Okay. Not eaten cake is true. So that will make this eaten cake available you, or you can ignore that part also. Because there are two techniques. One of the technique is you don't consider negative literal. Okay. Uh, or you consider this negative literal. Only sometimes you consider only positive literals, or sometimes you consider both. So this particular method where this negative is also considered, that is called as CWA representation, closed world assumption. Uh, what is this closed world assumption? Closed world assumption says that if some predicate is not given to you, then you assume that it is false. For example, eaten cake is not given initially at P0, so you assume that it is false. This is called as closed world assumption. This is something like this. For example, if the thing is specified, if you are suppose describing the current situation, weather situation. Suppose it is not specified whether it is sunny or cloudy. Okay. Whether it is sunny or not, just simplify it. Whether it is sunny or not today. If it is nothing specified, then you assume that it is not sunny. That is called as closed world assumption. That is one way, or another way of working on this problem is you only work on positive literals. So don't worry about this. You can go in any of the method. So eat cake, just now you told me that action you can perform. So precondition is have cake. Eat cake will result in not have cake will be true, and eaten cake will be true. Okay. So we have added this two prepositions in preposition layer P1. How? From the actions which are given. Eat cake we have added. Effect is not have cake and eaten cake. Now extend this graph. So what we have done, no of operations have been added. So have cake is available out here also, and not eaten cake we have made it available here. Why it is required now? You go back. This bake requires you not have cake. Okay. So therefore, this not have cake we have. So we can add that particular action out here. Along with this, now let us work on that mutex part also. We have to identify mutex actions. Okay. So what is this? This is no operation, and this is eat cake. Identify why they are mutex. We have added this mutex relation between these two. Why is it so? If you perform this first no of operation, result of execution of this operation is have cake. If you perform it at the same time, because they are in the same layer, at the same time, it is a discrete time execution. So if you perform each time, that is resulting in not have cake. So if this is preposition P, this is not P. Inconsistent effect. If you perform first operation, no of operation, you are getting have cake. If you perform eat cake, you are getting here, we see the link, not have cake. So either of this has to be executed. So there is a mutex link between these two. Reason is inconsistent effect. Okay. Now consider these two. They are also shown as mutex actions. Why? Again same reason. If you execute eat cake, one of the result is eaten cake true. If you perform this no op operation, then effect is not eaten cake true. So either of this has to be performed. If you perform eat cake, then eaten cake is true. Either you perform this first or you perform this no op, that will result in not eaten cake true. Both cannot be executed at the same time because that will cancel the effect. So that will be a useless execution. So here mutex relation is shown between these two actions. Okay? So in this way you have to add mutex relations between the actions and prepositions. So if two actions are mutex, corresponding prepositions related with them will be mutex. So let us extend this graph again. What we have done, we have added one more action layer. Bake cake action has been added out here. For bake cake, what is the precondition? Not have cake. Precondition is not have cake, and effect plus is have cake. So have cake is true out here. See, understood? So we have extended this graph to the next level. In this way, you keep on going further. This is how we develop a planning graph. And after incorporating a layer, you have to identify mutex relations at each action and preposition layer. Understood up to this point? This is one part of this graph plan algorithm. That means development of plan graph. You keep on doing this until yes it levels off. That means you reach to the preposition layer where all goal prepositions are true. That can be the terminating condition. Or two consecutive preposition layers, they are same. In that case also you can stop extending this graph, then extract the solution. If you get the solution, then algorithm will terminate. If you didn't get the solution, extend the graph again for one more level. Any question up to this? Only one part we have understood, that is how to develop a planning graph. Second part we will discuss after this. That means extraction of solution from this planning graph. So later on I have again extended this, added mutex relations between prepositions and actions. Now to understand this, again consider one more example. I will go through this example fast. At home you study this in detail. This is a problem, a popular problem of changing flat tire of your vehicle, your car. That is, what is the problem? Changing flat tire. Tire is punctured, so you have to change it. So robot is performing this task, suppose. So you will have to write a program, simplified version of that situation we are trying to model in the form of program. So initial state given is flat tire is on axle and good tire is in the trunk. Goal state is you have a good spare tire properly mounted on your car's axle. You are traveling and suppose your tire is flat, your car's tire is flat. So that is the initial state. Also given that we have good tire with you. Goal state is you are going to install, you means robot is going to install this tire on your car's axle. How to put it in the form of program? Initial state, you here put it in the logic form that two predicates two predicates we have defined. One is the flat tire is on axle, that is true, and spare tire is at trunk, that is given. Go back. Flat tire is on axle and good tire in trunk, that is given. Okay, so that is the initial state. Goal state, spare tire is at axle. So your robot has properly mounted that spare tire on axle. That is the goal state. Four actions are provided that robot can perform. One is remove action, which removes spare tire from the trunk. Another one is again another remove action, but that is different. That removes flat tire from the axle, because both these actions are different. Removing spare tire from trunk is different, and removing flat tire from the axle, that is different work. Then third action that is available with us, spare tire that is put on the axle, that is put on spare tire on axle, and another one is leave overnight. Now consider first action, understand these actions. To remove spare tire from trunk, the requirement is spare tire should be at the trunk. If you perform this action, result will be spare tire will not be at the trunk and spare tire will be on the ground. Okay, so it is at ground. To remove flat tire from axle, requirement is flat tire is should be at axle. Result will be flat tire is not at axle and flat tire is on ground. Put on spare tire on axle. Requirement is that flat tire should be at axle. Effect will be, result will be that spare tire will be at axle and spare tire will not be on ground. Leave overnight, no precondition defined for this. Effect is spare tire is not on ground, spare tire is not at axle, spare tire is not at trunk, flat tire is not at ground, and flat tire is not at axle. So these four actions are given, initial state is given and goal state is given to you. Now develop a planning graph for this. So start with layer P0. What set of predicates we will have in P0? Yes, P0 will contain set of predicates which are true,
At flat axle
right? Flat at axle
and at spark.
and at spare trunk. Yes, and second preposition predicate will be spare at trunk. because initial state is given to you. So these two prepositions are true, so they will be at the initial state. So same thing we have done. Spare at trunk and flat at axle. Both are true, they are in P0. In addition to this, this not at spare axle, not flat at ground and not at spare ground. Later on we need it. So therefore we have defined them in P0 because not spare, spare is not at axle, spare is not at axle, that is true. This is the goal that you have to achieve. Initially it is false, right? So therefore you can assume that that is available with you, not spare at axle. So in this way, other two prepositions they have been added because they are not flat at ground, that is true. Flat is not at ground. Initially flat is at axle. Spare is not at ground. Where is spare initially? Spare tire is where? CWA, closed wall assumption we are following. Spare tire is at P0. Go back, what is given? Spare tire is good means what? Good means spare. So where it is? It is in the trunk. So therefore spare tire is not at ground. This is also true. Okay. So now identify set of actions which you can perform with available predicates. So three actions have been identified: remove spare tire, remove flat axle, and leave overnight. Now let us find out first one. Remove spare from trunk. What is the requirement for this? Remove spare from trunk. Precondition is spare should be at trunk. So spare is at trunk, that is available. So you can of course execute this, and after execution of this, what is the result? So after execution of this, result is that spare tire is at ground. That is true. So spare tire is at ground. See this line, this edge going down. It has come here. Spare tire is at ground. So this edge has been added with this preposition. Okay. And one more effect is there, that is spare is not at trunk. Spare is not at trunk. Another edge going this way. Spare is not at trunk. Either this way you can do, or here instead of this two you can have a single preposition, and your in that case your edge will be like this, line with circle ending with a circle. Okay, that is one way of representing. In some books you will find out it is done with this way, or instead of that you can have separate predicate defined, not at spare trunk. In that case you will remove this, you don't need now that dot at the end of that line. Okay, either this or another convention is you add a link like this. In that case what will it will look like, only instead of two you will have only one now preposition, at spare trunk, in this way. But this way also you can do, separately you can show them. Second action has been added, remove flat tire from action. axle. Requirement is remove flat from axle. Flat tire is at axle that is available. Flat tire is at axle that is input to this action. If you perform this, what is the result? Flat tire will be on the ground. Check out. Flat tire is on the ground. See this link here. This is true. And second effect is flat tire is not at axle. Flat tire is not at axle. Right? So in this way, you keep on adding actions and extend this graph until it levels off. So I have done that. You check it at home. Graph is extended for the next level again. Okay. Now you find out, check out mutex relations also, add those mutex out here. For example, now why these two are mutex? What is the reason? These two actions are mutex actions. If you execute first action, result is not at spare is not at ground. If you perform second, result is spare is at ground. So this is P, not P, and this is P. So inconsistent effect. This is because inconsistent effect. Similarly, now why these two actions are mutex? Remove spare from trunk and leave overnight. These two. Again inconsistent effect. If you perform remove spare at trunk, one of the effect is that spare is at ground. If you perform leave overnight, then one of the effect is that spare is not at ground. So this is P and this is not P. So inconsistent effect. Because of that, these two actions are not, they cannot be performed at the same time. So they are mutex actions. So in this way, you continue further, add mutex relations, okay, and complete the graph. So complete graph will look like this by adding all mutex relations. And now let us find out the second step. Second step is how to extract the solution. That is more important, that we have to understand from this planning graph. What is the goal? Let us go back. Goal state is spare is at axle. So in the final planning graph, we have here a goal that spare is at axle. You start with this, okay, and go back. So that leads to the action put on spare on axle. This action. Again you go back. DFS you are performing and backtracking you are performing. You are going back. You are moving backward. So this is connected with two prepositions. You draw the line along with those. So one is flat is not at axle and another one is spare is at ground. Now again you go back, move backward, find out the corresponding actions to which these two prepositions are connected. So red line shows one of the action is remove flat from axle, and this second preposition spare is at ground, that is connected with this second red line, remove spare from trunk. These two actions, so they are shown in the red color rectangle. Go back again, so that has led to two prepositions in the layer P0. One is spare is at trunk and another one is flat is at axle. Okay, so now this is the solution that we have extracted. Go back, let us recall that step. Backward search call will terminate either by reaching to the level P0 with a success. Okay, so out there we have terminated that search at layer P0. So backward search we have performed. So this step we have performed before that. When all goal preposition exists in the layer are non-mutex, only one preposition was there. One goal preposition was there. What was that? Goal preposition was this spare is at axle. So process says that perform depth first search, which will regresses the goal state to the sub goal states like backward state space search. So same thing we have performed here, backward state space search we have performed, and finally we reach to P0 and corresponding prepositions are these two. So now this will tell you the sequence of actions that you will have to perform to reach to the goal. So result is you perform this remove spare from trunk, this step first, remove spare from trunk. Now we know that these two should not be mutex, and of course this is true. This is also red because we have backtracked. So this also you will have to perform remove flat from axle. So you either perform this first or this first, no problem. You can remove flat from axle first and then you can remove spare from trunk, or you remove spare from trunk and then remove flat from axle. Then you see the red lines, follow that, then put on spare on axle. That has led to this action, put on spare on axle. That's all. So if you perform these three actions, then you will get the goal, that is spare will be on axle. So what are the steps? Again I am repeating: remove spare from trunk, then remove flat from axle, and then put on spare on axle. Either this is the solution, or remove flat from axle first, then remove spare from trunk, and then put on spare on axle. So this is the solution your plan has resulted in. So let us summarize. You will find out the prepositions, number of prepositions, they increase monotonically in this planning graph. Actions also monotonically increase. Preposition mutex relationship, they monotonically decrease. Action mutex relationship monotonically decrease. So number of prepositions and actions they increase, but number of Mutex relationships, as you proceed further, level by level, they decrease. Remember this. The planning graph levels off after some time k, all levels where will be identical because it's a finite space. Set of literals never decrease. Mutexes don't reappear. So that you check out from the example, and this graph length always returns the optimal plan. Okay. Any question?
No, sir.
This is actually one of the very good application that you can visualize, because most of the topics that we have discussed, that was required uh, to develop an AI system. This is a specialized area topic in AI where you can visualize the actual application of artificial intelligence when you are going to program robot. For robotic application, such a uh, knowledge representation as well as problem solving technique you will have to incorporate so that robot will work intelligently in the real life situation.